Good evening, everybody. It's a very great pleasure to be here, and it's sort of an interesting historical connection because the Philosophical Society was founded in the same year as the Cambridge Observatory by many of the same people with the same aims to try to encourage the study of physical sciences in Cambridge and innovative ways of analysing observations. And that's precisely what we do, and it's precisely what I'm going to talk about today. So I'll start with a very brief history. One of my colleagues famously wrote a brief history of time, but in fact you can do better than that. Instead of needing a whole book, you can put the entire history of science on one slide, which it is here. And the key aspects of this are on the left-hand side. There's Newton, of course, and underneath that there is a page from his manuscript of what would have been the last edition of the Principia, and this was a description of his model of the Milky Way. And Newton, being Newton, had worked it all out, written out all the words very neatly in Latin, of course, and left space for the diagrams and the tables of numbers to prove that the explanation was correct. And you can see what happened when he started putting in the numbers, is they didn't work at all. And the numbers were the relative numbers of stars of different brightnesses that have been available since classical times. And in fact, that's one of the strange things about astronomy, as we'll come to in the next slide, is although it is the oldest of the technical subjects, many of the clay tablets in the British Museum are actually detailed studies of the prediction of eclipses and so on from 5,000 years ago. It's only very recently that it's really taken off as a subject. But anyway, what Newton was trying to do was explain the relative numbers of stars, and it didn't work. So Newton, being a typical Cambridge theorist, said, well, there's something wrong with the data. And so he binned half the data, and that still didn't work. And so then he did the next thing that any Cambridge theorist, and I'm saying this because several of my colleagues are in the audience, would do. He said, well, theorists are just no good, you can't trust them. I mean, observers are no good, you can't trust them. So there must be something wrong with the observers. And he deduced, in fact, from that the human eye is not linear, but is logarithmic. And so the relative numbers of stars should be logarithmic rather than linear. And that's true. It's why we're able to see at night and have night vision and so on. So he deduced this fundamental property of the human eye based on the assumption that observers couldn't be trusted to get their numbers right to match him. And that improved things a little bit, but he still didn't get it right. And the reason being that he knew for an absolute certainty that the model of the picture of the universe that he was describing must be that made by God, and God made only mathematically perfect things. And so he solved the minimum packing problem along the way and predicted the number of stars that you would get in a perfectly uniform distribution in space of stars. That still didn't work. So two things happened then. The first is that he was contacted by some colleagues who said, this is dynamically unstable under your own gravity theory. And the second thing was he gave up astronomy and gave up science, actually, and went off to run the Mint. And so he simply couldn't get beyond knowing the answer and trying to fit it into the observations. The real progress happened with these two, William and Carolyn Herschel, a century later, just on a century later, in which they actually went out and counted stars. They're the only people I know of in the history of astronomy who do that cartoon thing of actually looking through a telescope and counting stars. But from that, they deduced that the Milky Way structure must be something like this. And that's not bad, actually. That's not far off. And so the fundamental lesson that we all learn there is that the way to make progress is to do experimental philosophy and not natural philosophy. You look at the data and see what it's telling you, rather than have a model which you're going to project on the sky. Now the next slide I don't expect you to read or even look at very closely. It has one numbered line in it that I'm going to point out. And that's to put in context where we are now, because it is the 100th anniversary of this 1920s line. And it was only 100 years ago this year that mankind realized that the Milky Way was not the entirety of the universe, that we were just one galaxy and there were lots and lots of other galaxies in the universe. So everything we know about the universe is actually extremely modern. It's post-1920. So that's really when the science of astronomy started. And then things happened, you don't need to read it, but every decade there was a substantial advance beyond that. So after 5,000 years of stasis, things took off a century ago, and so it's a good time to be doing astronomy. The other thing to remember is that space is big, and so the numbers we use in astronomy are just ridiculous. So don't expect to understand them. We don't either. We just pretend. The numbers are just too big. You just have to take them at face value. But now it's a very sort of easy beginning introduction. What are we talking about here? Well, a top-down view of our Milky Way would look something like that. But we don't see it top-down. We see it side-on since we live in the middle of it. And so we see it something like that, which is a warped, twisted plane. So this is our view of the sky. So this thing is the Milky Way across the sky as it would be seen from outside. And that's what we have to work with. And this is the cartoon model of the same thing, and again showing you the time scale on which we're working. So we know that the central region of the Milky Way is called a bulge, and right in the center is the center with a big black hole in it. And then the Milky Way itself is this disk that covers the whole sky. We're out about here, about 2/3 of the way out. And then the whole thing is surrounded by a thicker disk of old stars, and then a huge extended halo with roughly these numbers. But to put that in context, the thick disk was discovered only in 1983. Up there. So our modern understanding of the basic structural components even of the Milky Way is very, very modern. And what these structures are, of course, are remnants of the physical processes, and that's what we try to determine. We'll get to that later in the talk, of the physics that goes on to create this rather complex looking structure and eventually what it's going to turn into. Now, the thing that underlies it, of course, as I started with Newton, it's Newton. And so here's Kepler's laws, actually, but that's Newton. Up there, the relative distance versus the orbital period suitably scaled of planets in the solar system. And you see they lie in this perfect straight line. But the interesting thing is that doesn't apply in galaxies. And this is a great discovery of the 1960s when radio astronomy was discovered. In particular, a person named Morton Roberts showed that for the M31, the Andromeda Nebula, which is this thing, that the speed didn't follow this blue curve, which is Newton, but stayed high, way beyond where there was any light. And so there must be the majority of the mass has to be out here. And that was really the realization that dark matter, missing mass, dominates galaxies as opposed to just exists in the universe. And so that was a really huge step through. And just again to put that in context, this is what was expected. So this is what happens when all the mass effectively is in the sun, all is at the center, and as you go away, the speed slows down according to that line. But that's not what happens. Galaxies are made of stuff that dominates the mass, and so now we go beyond the Herschels and say, okay, this is the galaxy that we see. We now can have a picture rather than just the drawing they had, but this is what is there. And so the summary is that ordinary matter, the stuff that everything that we see, is this little almost irrelevant yellow bit here. So all the physics, chemistry, and so on, all of our existence is in this small part. There's another form of matter about which we know almost nothing, except that it understands gravity, and so it's matter. And there's about 5 times as much of that. And then there's this. The whole thing is dominated by a different form of energy. We're not going to talk about that today because this manifests itself only on very large scales. But this is the negative pressure, the anti-gravity pressure that controls the entire universe and is causing the universe to accelerate apart. But the other, again, introductory part of where we're at, what does our local universe look like? What are we trying to explain? Well, up here, this is a sort of 3D type sketch. The Milky Way here with its satellites forms one group of little galaxies, and there's another one over here, our nearest neighbor Andromeda, with its group of satellites, and the two of them are falling towards each other. And so this is the entirety of the local universe as far as we're concerned, and the two parts of it are falling together at this speed, and in a few billion years will meet, and that will terminate the story. So we'll come to that at the end of the slide. So this can be all put together, in this sort of cartoon calculation of what is the history of the universe, and you can see it here. So you can see as time is going on here, this is time in units of billions of years. So you see the universe started off very smooth. It had sound waves in it, and those sound waves produce structure. So although people think that the Big Bang is just a silly name, it was a bang, and the universe was full of sound waves. And those sound waves, the peaks of those sound waves, fell together and they create all this structure over time. And then you start to form things that eventually end up looking more or less like galaxies. The key thing is this list down here is the list of ingredients, and that's this pie diagram I showed you. If it weren't for this relative contributions for things, this is not what we would look like. And so now you see a galaxy a bit like the Milky Way, and you see it in its later life. You see it being smashed to pieces by things falling in, and it's slowly growing and evolving. I won't, you can do this in all sorts of parameter space. So I'll go beyond that. The key thing is that is the state of the art in calculation. But of course, what we're interested in is what nature did, so that we can inform the modeling and improve it. And in fact, that isn't what the Milky Way did. So the best state-of-the-art calculations we have the Milky Way as an extremely unusual event. There's probably 3% chance that the Milky Way actually exists, according to these models. But we're pretty confident it does. And so the idea is to feed back that information to the modeling. And so how do we do that? Well, how do we go about solving a problem? It's true in most things, but the way we do it is to try to duplicate what our minds do when we solve any problem. And our minds, although people get confused by dimensions and so on, say 1D, 2D, 3D, and after that gets complicated. In fact, our minds work in approximately 40-dimensional space. And the way we describe that normally is from our senses. So from each of our senses, we deduce information and we put bad labels on that information. So for example, repeated with what we're talking about now is speed and motion and change and variability. Or if you listen to something, you can tell the difference between different types of source of that sound. And all this information is being stored in your brain. Most of it goes into your subconscious, so you aren't even aware of it. But your memory comes back as a multi-dimensional video with add-ons. It's something that Meta aspires to copy. So all that information is there. And that's what we're trying to do in astronomy as well. So in the same way that there are many different dimensions, dimension in this sense simply means a property that can be changed independently of all of the other properties. So for example, for most things I can change color independently of speed and so on. And that's what we do in astronomy. And so we take the information we can find for everything that's independent of everything else, and we stack it up into this high-dimensional reality. And then we have this hypercube, a high-dimensional hypercube, and then the challenge is to look through that in whatever dimensional space that you are able to investigate to find structures, correlations, and information inside this multi-dimensional space. So you might, for example, quite readily discover that distance was correlated with some other property like chemistry of stars, or you might discover that ages were correlated with position or something like that. And so these are all the types of correlations and properties that one goes looking for. And you do this in this hyperdimensional space, which you can either do by projecting time after time after time, all the different possible dimensions against all the other dimensions, but of course that's a very high order parameterization. Or you can just be incredibly clever, or you can be very lucky, or you can use standard model artificial intelligence systems who will go searching through this 40 to the power 40 space for you and look for whatever it can find inside there, and then you can try and make sense of it. And so that's the challenge that we have, is first of all to obtain the reliable information, and secondly to try and make sense of it. So I'll just skip straight over the next slide and go on to how we now talk through a little bit of the history of how we came to do this sort of thing. And so an example was combining photometry. So the colours and brightnesses to determine distances and speed, spectra, radial velocities, and so on. And this led to the first discovery of stellar streams in the early 1990s. And here is it, actually. This is the first one. And you see that looking at the velocity and distance of stars that should have been randomly scattered over this diagram. The idea was to measure the random velocity dispersion in the very outer parts of the Milky Way. But it turned out that there is clearly a little stream across there, a little clump of stars that all know about each other. And so this was the first suggestion that actually there's information out there in the outer parts of our galaxy, if you look in the right part of parameter space, that will be telling you something about the history of where those stars came from. And so it's the suggestion, therefore, that what we're looking at here is the remnants of some structure that has evaporated over time. And so we've still got the trail in kinematic space from conserved quantities of something that was originally a different structure. That took off in a decade later, or a few years later, with this particular stream here. And so you see this is again a distribution. This is looking into the inner regions of the Milky Way. This is what one expects to see, stars moving all over the place, and that's what you wanted to try and model. But in fact, you discover a very large number of stars that are moving at almost all exactly the same speed. And so this is regardless of their colour. This is colour along here, so even red ones and blue ones. So there's a large number of stars all moving at the same speed. What is this? What's going on here? And this was the first big advance in the subject. What it was the discovery of an entire little galaxy called the Sagittarius dwarf galaxy, which is deep inside the Milky Way. It's named Sagittarius after the constellation, so this is a picture of the southern sky, with Sagittarius being the constellation that includes the central part of the Milky Way. And this little galaxy is what we found there. Well, it's not little, it covers a big chunk of the sky. And so this was a really game changer at the time. It unfortunately became very popular in the US, and they used this horrible phrase of smoking gun. Particularly given topical circumstances, that's a regrettable phrase we could do without. But anyway, this was touted at the time as this is the evidence that galaxies still grow in late times by accreting smaller galaxies. And so here's a sketch. You can see the origin of what was actually going on. So there's us over there looking back past the middle of the galaxy, and here's this part, and it's tidal tails stretching around the sky. Now that turned out to be true in this beautiful picture developed by Vasily Belukharov, who's sitting in there, of these two amazing streams. Now this is a really clever picture. This is what you can do when you suddenly have digital data. So by the 1990s, we suddenly had digital maps of the sky. We didn't have to have photographs and do something. When you've got a digital map, you can adjust it by walking through parameter space. So this particular picture was taken by, first of all, removing all the galaxies from the universe. So you just take them all away. And then secondly, you statistically color code the stars by their distances. And so you can see that there's a distance gradient along there. And in fact, you see there's a double structure as well. And then in fact, I'll come back to this later on. There's also other things turned up. So there's another little stream going across there. And so this became the poster child for the way that the Milky Way is actually evolving. And so it was realized that the Milky Way must be something like this. There's the basic Milky Way, but it's got all this stuff going on around it, these trails. And these trails are the history of its formation. So there is still information available in structural space, in the outer parts of the Milky Way anyway, of where the Milky Way came from and how it evolved. And so finding and mapping these structures became a huge business, and is still a huge business, from which we try to deduce, we just run back in time. But this is all very well for structures that have come from somewhere else. This was an independent galaxy that just strayed too close to the Milky Way and was trapped by its tide. What about the Milky Way itself? How did we go about studying that? Well, the technique there is complementary. Again, it's working through dimensional space, but appropriately, given this lecture theatre we're in, it involves chemistry. And the interesting feature about the chemical elements is that apart from hydrogen, helium, and a little bit of beryllium, all of the chemical elements are made in stars. And they're made in stars with a variety of different timetables and a variety of different physical processes. So different chemical elements are made in different types of stars. So there's this color-coded here. This is the most recent trendy example of gravitational wave sources, create all the heavy elements. They're the dramatic things, but the more normal stars, the point is these things happen on different time scales. And so by looking at the relative contributions from these different processes, we have a form of clock, and that's the excitement of chemistry. So what you need to do is find a set of chemical elements that are made predominantly by one process, but with a little bit of another, and vice versa, things that are made purely predominantly in a different process and a little bit from the other. And so carbon and nitrogen are good ones, if I can find it. Magnesium somewhere in there is a good one, up here. That's a good one. Sodium. See, these are basically clean, simple things. But then you need something that's always there, and we use iron. Iron is the sort of, everything is connected to iron because that's created both very rapidly and very slowly. So this is a long time scale, slow process. This is really fast. It's effectively instant. On astronomical time scales, it's 10 to 100 million years, which is nothing. But counting the absolute number of atoms that have come out from a star, which is what you really want to do, because that will tell you not only how many stars form, but what type and what rate they formed, and would give you the perfect clock. That is a challenge for the future. We are not there yet. The next generation will begin to approach that. The only way we can do it is by looking at the ratios of things, because this is the only thing we can measure that's robust as of present. So it gets complicated because we have to talk about ratios. You've got to understand two things that go on. And so this is how ratios behave. They're really very simple, undersimplifying assumptions. And so if you take the ratio of something that forms only in very, very fast, short-lived stars, massive stars like oxygen, something like that, and something like iron that's formed partly in high mass, rapidly in high mass stars and partly more slowly. So you say, well, why do I need to have that mix of processes? Well, if you don't have something that's formed both rapidly and slowly, you don't have anything to ratio it against early in the universe. So if I have other ratios just don't exist down here. They only appear up there. So I need something that's always there, and so steadily builds up, and something that tells me how many stars are exploding today. And what will happen then is this ratio will be constant if the galaxy we're talking about is completely young, totally dominated by only very young stars. It hasn't had time for anything else to happen yet. So for the first few 100 million years of the life of a galaxy, this number will be stable and high. And then as time goes on, these other explosive processes, longer-lived ones, come in, and that creates extra iron without the extra oxygen, and so that dilutes this ratio down. And so the top level up here tells you how long the galaxy was in this very early state, and the rate at which it comes down tells you when it slowed up and came into a more normal equilibrium type situation. And the further you move across tells you how fast the rate of star formation was. So in a small, slow galaxy with not many stars forming, you turn down fairly soon. In a bigger galaxy with lots and lots and lots of stars forming and things being very exciting, you stay up for a long time and then come down later. And so this is the sort of diagnostic that we had available. And this is what it actually looks like in the real world. So you can see in this top diagram, this plateau level that I pointed out goes all the way along there. So this is magnesium and oxygen, same thing. And so you can see that these stars, which we now thick disk stars, formed rapidly, and they went up to quite high chemical abundance quite quickly. So there must have been a lot of star formation going on very quickly. Whereas the more normal disk stars formed on a much, much slower time scale. And so this really trivial illustration tells you that the thick disk formed rapidly and early on, and the thin disk, which is still forming today, is a much, much slower process and much more extended. You can do the same sort of thing for all the satellite galaxies of the Milky Way, and you see they're just a mess. They're all over the place. They're almost all much lower star formation than in the Milky Way, so they're all way down here. But there are two interesting things about this. First is it tells you that the satellites, like the Sagittarius, the galaxies that are around our own Milky Way are not like our Milky Way. They each have their own independent existence, which is not tightly connected to us at all. So they must be far enough away that they're independent. And secondly, that the average star in these galaxies does not look like the average star in the Milky Way. So most of the Milky Way has not been made by putting together other galaxies. Most of the Milky Way has been made in the Milky Way. So they're quite profound conclusions already, but that's just a simple 1D look at a diagram like this. Shows you how much information we can already deduce. Now, going on from that level of chemistry to this horrible looking complicated diagram, we can do the same thing now much more in a much more complicated way, or much more intensive way, in which you can use this the chemical abundance of a star and against its age. Now, ages are hard, but these are approximate and they're plausible. And you see what happens. Long ago, there were not very many chemical elements. That's fine, you expect that. And the number of chemical elements increased. So this is increasing chemistry. It means more stars forming. And that continued until around then. And then suddenly, all the chemicals went away, the iron. So now remember, I've been talking about ratios up to now. This is the first time I've shown you a plot with absolute number of elements on it. So this is real iron abundance. It's really hard to do this experiment, so it's not been done much, but it will be. And so it tells us immediately something dramatic happened to the universe, to the Milky Way, about 6, 5, 6, 7, 8, something like that. These ages aren't very precise, billion years ago, and that somehow all the iron got diluted. Well, you can't take iron away. You can't destroy atoms. What actually happened is that this is still a ratio. It's a ratio against hydrogen, the stuff from the Big Bang. And what this means is a lot more hydrogen suddenly appeared. So you dilute the ratio by adding more hydrogen. And so what this tells us is that there was a big merger of the Milky Way. Another galaxy that was still mostly hydrogen came in and merged with it and reset the clock, which then runs back up here again. So this is the state of the art from what one can do with chemistry. You can see also these are three of the ratios to justify what I've been saying all along. So there are some elements that are formed, this is old on the right-hand side here and time going on. See, there are some elements that are extra creation in the early universe. This is when the very first very massive stars were forming, and then they dilute down and the galaxy comes into equilibrium. There's some where the element ratio for these particular elements, they're always made in the same type of stars, so they're not telling us anything. And then there's others which are the other way around. They're made only predominantly now and were very rare in the past, and so you see them ramping up. So it's analysis of diagrams like this that allow you to draw those yellow bars. They're not very specific, so what one wants to do then is go on and get a lot of much more specific data. So this is the first example of a project that I will mention. It's called the Gaia ESO survey. It was a huge, big spectroscopic survey using these telescopes in Chile and these people. And it was an enormous project and was designed to provide this high quality data of the relative numbers of different elements in different stars. And it did. Over a decade or so, it produced the precision data for 100,000 stars, which were just finally published earlier this year. So the final results are just coming out now. But it's an example of how one can go on and do more sophisticated things. And here is one such example. This is looking at, in this case, distance from the center of the Milky Way, which is over here. So this is position in the Milky Way versus this ratio of how much chemistry there has. And as you can see immediately, this goes down. And so all that tells us at face value is that the inner parts of the galaxy have had more stars and more generations of stars than the outer parts of the galaxy. And that's not really surprising because that's where most of the stars are. And so as you go further and further out in the Milky Way, you're more and more primeval, whereas the inner parts are much more enriched. But the interesting thing is this is color-coded by age again. And so we look somewhere near the sun, where we are, about here, and we see that these are ages in 10 to the 8th years, 10 to the 9, so 8 means young. And so you see the young things have chemistry very much like the sun. That dot is the sun. Whereas old things don't. Old things actually have higher rates of chemistry. And so the chemistry has gone down over time, even though more and more stars have been forming. That's, of course, impossible in this situation, in this little patch of the Milky Way. And so what it tells you, probably, is that these clusters of stars, which are all very near the sun now, did not form there. They formed in the much, much further. You see, if you can imagine extrapolating this line all the way back in, when you get near the center, you'd be up here, and that's where they belong. And so this probably is evidence, in fact, it's quite good evidence, that at any given point in the Milky Way, stuff moves around, and it moves around dramatically. So half of these clusters near the sun have actually come from very, very far away, and they've moved out to where the sun is. And so things move around. So the galaxy is not a simple static thing. You can't just build it up in a simple, easy way. And in fact, if you do that same trick to the sun, you discover that the sun doesn't belong to where we are either. The sun is anomalous compared to its neighbours. And so we probably formed 1,000 light years or a few thousand light years further in towards the centre of the Milky Way and have come out. And so we are no longer where we were formed. And so this seems to be a perfectly normal process. It just adds to the complexity of trying to make sense of what's going on. Now there's another way of guessing ages. Now we're moving on to ages. Ages are hard, but we developed a statistical way of developing ages. When you do that, you can then move into very large numbers of data points. So instead of getting the 20 data points I showed on the previous thing, you can show thousands and thousands on the same data. And so what's coloured here now is this chemical ratio versus the total absolute chemistry. So this is time going along the bottom here. This is old, and they're going up to more recent. And then it's colour-coded by age. And so these are the thick disk stars. And you see the thick disk stars forming very quickly. And then that merger I already mentioned jumping back over here. And then the thin disk coming on from there. So the thick disk had a progenitor, whatever it was, up here, but the thin disk essentially sprang fully formed from Zeus's forehead about 6, 7, 8 billion years ago and started from here. And so this is the structural information we have as to what's going on. But then, of course, you want to say, well, what came before all of that? You know, I'm only talking about the disks of the Milky Way. What about the outer parts, that what we call the halo stars? And you see they're all over the place in this complicated looking diagram. Some of them join on to these very early stars, but others are down here. So the halo is obviously very, very complicated indeed from this diagram, and something really difficult happened with the halo. So there we need to move on and say, how do we start to understand things like that? For that, we need a new tool, and that is a tool that can measure speeds, motions, positions, distances, and brightnesses of stars very accurately, so we can start to unpick where they are and what they came from. And that tool was this, Gaia spacecraft. This is it being prepared for launch. You can see it, that's the top of the rocket, the fairing it's going to be called. And there's Gaia inside as they prepare it for its final journey. And there, one of the traditions that the European Space Agency has is to paint on these rather lovely fairing designs onto the outside just before they launch it. That's the first time you're supposed to see that picture, that sort of little girl pointing up at the stars, sort of sub-Banksy thing, really. And this is, while that's going on, the Russians are busy building your rocket for you. They come in a kit set, Soyuz rockets, and they put them together. This is in Guyana on the coast of Africa. And then they roll their rocket out, and then you drive out with your spacecraft, and it's now in its little case, and you lift it up. Here it is coming up, and you put it on top of the rocket. So that smooth thing there, that's the rocket. So you stick it on to the top of the rocket, and you're ready to go. Then you step back and light the fuse. And hey presto, off it goes. It's a truly moving experience, actually, seeing your 15 years of your life's work sitting on top of an exploding bomb. However, fortunately, they're the Soyuz rockets, the same ones that put Gagarin into orbit. We were launch number, I think, 1678 in that series, and they just don't fail. So there's an interesting complementarity of technology. The Russians learned how to fire rockets up reliably in the 1950s, and they've just done the same thing ever since. And everybody else has built stuff and lost the technology, and built stuff and lost the technology. But anyway, that was the really big step, and that was Gaia, which changed everything. What Gaia is two telescopes that measure the distances to stars. They do it through the same way as you measure distance with your eyes, with parallax. The only clever thing about Gaia is that there are two telescopes, not one. And the reason being is that if you use a normal ground-based telescope, which you could do, and people have been for centuries, then you can measure over the year, as the Earth goes around the sun, a star will appear to move in a little ellipse on the sky, a big ellipse if it's close to us, or a small ellipse if it's far away. And the technique that astronomers had used for a very long time indeed was to measure the distances, the relative distances to nearby stars and distant stars, but all you could do is measure relative distances. You've got no 0 point. All you're doing is measuring differences. But if you have two telescopes looking at the same field of view with a known angle between the two telescopes, then the star seen in the second telescope is going to have its ellipse tilted by exactly that known angle. And so the angle between these two ellipses is then a known quantity because it's just set mechanically. And so you can solve for the whole thing and get distances for every star. It's a superficially simple concept, but this is in fact the path of a star. This is the calculation of the apparent path of the sun on the sky as seen by Gaia from 30 light years away. And so you can see this loop structure. Well, you see the first thing you notice is this motion across the sky. That's called proper motion. That's the orbit of the star in the Milky Way. The second thing you see is this superimposed loop structure, and that's the parallax. And so measuring that angle tells you the distance. And the third thing you notice is these wiggles and bumps and things. And that's caused by the planets. The sun isn't the center of the solar system in that sense of the word. It's the center of mass. But because, particularly due to Jupiter and Saturn, the sun actually is orbiting about a point above its own surface, and so it moves as well, and one can see that movement in these wiggles. And so from the same information you can deduce the existence of Jupiter and Saturn, possibly even Neptune if you keep going for long enough. And so Gaia not only measures the properties of the stars, it measures their environments, and that's still to come. But what Gaia really does is produce a prodigious amount of data. And to handle a prodigious amount of data, you need a large number of very clever and unbelievably hardworking people. And here is the Cambridge contribution to that. So the reason that Gaia works is because of these people, not just because of the technology. But again, to show you the fairing, you see there's the little girl looking up at all the stars for the given different colours. It really does look, to be honest, like that Banksy picture of a balloon flying away. But nonetheless, it is our logo, and we know and love it. So this is what Gaia is for. This slide I do like to show because it's of historical significance. In the year 2000, about this time of year, the Gaia mission proposal, which by then had been through 5 years of detailed industrial study, and so had been worked out as a costed engineering feasible project, was presented to the European Space Agency Commission community, all the accumulated committees and national representatives and all the people going to fund to it, in a huge meeting which was held at UNESCO headquarters in Paris. And this is the slide that I used to present Gaia to that meeting for its approval. And so this is what we predicted we would be able to do. And so there are several things about this. The first is you can see how undramatic PowerPoint was in the year 2000. This was state of the art in the year 2000. We had to get a special pre-release beta license to be allowed to use it like this, but it was still pretty crude, but at least we had dashes and things. That was all new. But anyway, I know I won't read all this, but the thing is we knew that Gaia would do all these things, and trying to do, and that's what it did. In the interest of saving time, I won't show you this, but this is a movie of the Gaia motions. This is a corny quote I stole from Galileo, I couldn't resist it. But each of these tracks is the predicted motion of a real star. So this is the whole sky is dynamic, and this is where all the stars on the sky are going to go for the next 3.4 million years. So you see everything is moving at the Gaia level of precision, everything. And so that means that one can use this information to say, well, where are these stars? You can also run the clock backwards, at least when you're away from the messy bits where too much dynamical scattering happens. But out here, life is calm, and so you can run this stuff backwards, and you can look for clusters and clumps, and you can look for things that are moving together and deduce from that how the galaxy was put together. There's one rather really dull slide that I'd like to show you now, which is just because we're all so proud of Gaia. The funding agencies, people who spend a lot of money on putting up spacecraft. So Gaia was middle, well, it wasn't middle, it was the smaller end of the big space missions. So it cost about €1 billion. So that's cheap compared to James Webb or Hubble or something, but it's not peanuts. And so what the agencies do when they build these spacecraft and put them up there is they track the scientific impact. And this is the parameter space that is used to say which technical papers appear in the technical literature which depend on that spacecraft, because that's a measure of how many people are interested in using it and so on. And so this one here, this is the Hubble Space Telescope. And you see it was always been much more popular and higher impact than other things, and over time it crept up and crept up and crept up until today it's about there, producing about 1,000 publications a year. And this is Gaia. And so Gaia is the ultimate good value for money, high impact science. So we're all proud of that. So anyway, now back to what one does with Gaia and so on. Once you started to add kinematics and so on to what is going on, this is where one starts to look at what happened in the very early part of the Milky Way. So the first thing that one could do is just say, let's just look in Gaia at the relationship between brightness and colour for all of the old stars. And then the Gaia data is so precise that you can see just by looking, there's two different group types of stars there. So the old stars are not a single population. What are they? Well, the precision data is such that it's so extreme. But to make sense of that is not trivial. And so this is state of the art for what is going on now. But the basic conclusion you came out of this is that unfortunately people give their discoveries either very esoteric names or very down-to-earth names, depending on who you are and what you do. And this particular, the most exciting part of this was called the sausage, which isn't a name designed to sort of win plaudits in the poetry community. But anyway, what is plotted here is the speed of the star around the center of the Milky Way versus the speed in and out from the center. So you see it goes in and out from the center versus round and round, depending on which way it's spinning. And because the disk of the galaxy is going round and round, all the disk stars sit up here. So they don't go in and out very much, but they go round and round a lot. And so stars like our sun live up there. But when you look at this distribution, what you see is, if you cut that away, what you see is this distribution here that's rather sausage-shaped, hence its name, in which the stars are not moving round and round at all. They're moving preferentially in and out. And even more importantly, they're moving preferentially in and out with quite a sharp edge to what they do. So this means that these are the stars that are moving now up to 3 dimensions. These are the stars that are in 3 dimensions around the Milky Way, and out to, in fact, a number that corresponds to 30 kiloparsecs, or about 100,000 light years. The majority of the stars are moving preferentially in and out, What that means is that these stars were in a separate galaxy that came in and merged with the Milky Way. And it went pretty well through the middle of the Milky Way, got completely destroyed by the tides and the Great Merger, and just they're still there, carrying on, going in and out and in and out. Now we know from the chemistry, of course, that we needed something to come in and give us all that hydrogen to change the chemistry, and hey presto, here we know. So this is the thing that came in and produced a total change in the chemistry by adding a whole lot more hydrogen, just a little bit before our sun formed. So in a funny way, our sun is a descendant of this stuff as well as that stuff, so we can see both our parents. Looking at it in a slightly more technical way, you can see these blue stars over here. Some of them run into the thick disk, and some run down here and then sort of stop. Nothing comes further in than that. So this is the early history of the Milky Way. I'm not going to go on in detail about this because it is a state-of-the-art subject. It's changing by the day, and it deserves a whole talk in its own right. But what it does mean is that we are now able, thanks to Gaia, to actually unpack in impressive detail the entire early history of the outer parts of the Milky Way. So we can say what actually happened and when it happened, rather than simply speculating. Now the other thing we can do is go and look at these streams that Vasily discovered, these Sagittarius streams across there. And the interesting thing, when you can look at the motion of these streams with Gaia, instead of just seeing where they are, you can see how they move. And a star, if this is just the tides from the Sagittarius dwarf being ripped off, the stars should be just moving in the galactic tides, so they should follow basically the shape of the dark matter halo. But in a very clever piece of work, it was discovered that they don't. They're actually moving sidewards a little bit. And it's impossible for them to move sidewards without some force to move them. So there must be some mass that is moving them. And hey presto, this turns out to be our biggest satellite galaxy, the Large Magellanic Cloud. And so the solid lines here are where things ought to be, and the data points are shifted. And so what we're looking here is a torque, a transverse torque on the outer parts of the Milky Way, which comes from the Large Magellanic Cloud. And so this produced a truly astonishing picture of where we are in the modern Milky Way. So this out here is Sagittarius and its tails going along. This in here is the Large Magellanic Cloud cruising past and torquing everything. And in the middle is our sun going round and round the centre of the Milky Way. But the intriguing thing about this dynamical interaction is because these galaxies are actually fairly massive, they're maybe 10 or 20% of the total mass of the Milky Way, they actually perturb the Milky Way. So the centre of the Milky Way moves. You'll see it now in this iteration. You watch the centre. In the centre, as the Magellanic Cloud comes in, you see the centre is getting pulled out of the way. And so this is telling us that the entire centre of the Milky Way, all the stuff we see, is actually sloshing like a pendulum inside this gigantic dark matter halo. That we think of what we see as what you get, but it isn't. The whole of the visible central part of the Milky Way is sloshing like a pendulum, driven by these dynamical interactions between our companions. So the whole thing's incredibly dynamical and vibrant. It's really quite spectacular. That I'll leave Vasily to give a whole talk on in the future because it's such impressive work. Or Eugene, who actually made that movie. Now, it's another thing that we get from Gaia to say, well, what can we say about the dark matter itself? And there's a long-standing challenge been for astronomy to say, how is the dark matter distributed? In principle, it's very simple. That's the measurement up there. It's just a pressure, mathematicians, the audience, physicists will immediately recognize just a pressure-gravity balance equation. There's nothing sophisticated about it. And so this is gravity over here, this is gravity. And over here is pressure. This is the dominant term, and there's a couple of stress terms which are small, so that don't matter. This is the dominant term here. And so that's dominated by the way the density of stars falls off with distance and the speed of the stars, which provides the pressure. And so that's that term is actually pressure. Now, we've first worked out how to do this properly back in 1989, and just out of curiosity, overlaid that on the recent Gaia data. So what's plotted here is actually the number of stars. This is the galactic center, galactic plane here, and this is the number of stars to the south and to the north falling away over distance, with this velocity now known, and therefore this being a pressure gradient. And so from that one can calculate how the dark matter is distributed. But the interesting thing, you then say, well, hang on, Gaia's just told us that the galaxy is a very dynamical and complex place, and so it can't be that simple. And in fact, it's not that simple. One of the most dramatic discoveries is if you look closely at any patch in the Milky Way, in the plane of the Milky Way, the stars aren't just going up and down randomly, they're actually moving in spirals. So they spiral up and they spiral down. And so even our sun does this. This seems to be an artifact, or not an artifact, a consequence of good old Sagittarius galaxy again. As it crashes through the galactic disk, as it's approaching, it pulls stars up, and so pulls them up away from where they normally would be. They're still going round and round in their local angular momentum, but they're pulled up, and then the Sagittarius flies through the disk and they're pulled down again, and so they start moving in a spring-like spiral. And because the dynamical timescale of Sag racing through is so short compared to anything else, it gets left there as a history. So you think, well, okay, so everything's moving in a spiral, then something like the virial theorem is not going to work. But it turns out that this is actually has hardly any effect at all. And so what we've always known about the distribution of dark matter is still the case. Now, I'm nearly finished. I will stop very soon. So this is just the history of the measurements of the amount of dark matter over time. So you see it started there. We first learned how to do it back in 1990. And since then, all these independent determinations, everybody's always got about the same basic number. And so this is the density of the dark matter. It's about 1/100th of a solar mass per cubic parsec. I've told you astronomy numbers mean nothing. That will mean nothing to you. But in terms of physics units, that corresponds to this. Now, a GeV is the mass of a hydrogen atom. It's the mass of a proton. And so that tells you the local density of dark matter is about 1/3 of a hydrogen atom per cc. And so it's not much. It's just that the stuff is everywhere. If you compare that to the local density of hydrogen atoms, which is an Avogadro's number, then this sounds like it's utterly insignificant. But the only way it wins is that there is an Avogadro's number of hydrogen atoms only on the Earth. Out between the Earth and between the stars, there's almost nothing. And so this stuff wins by the volume, and so this becomes dominant. But it's surprising how well we know this number and how it hasn't changed now over 40 years or something. I mean, this is the constraint on how much of it is, but we still don't know what it is. Now, I will end by reminding you that although pretty well everything I've told you up to now has been based on trying to understand 30 or 12, 20, 30 dimensional space by projecting through it in very clever ways and looking for signals of things that you might know, there are new ways which are actually old ways of studying this. And one way we're trying to do is following Darwin, very appropriate for this sequence in this place, from this now returned diagram, his tree diagram. And this is a well-established methodology in anthropology and biology. And so you think if it works for working out the evolutionary history of people and plants, it must work for the evolutionary history of stars as well. Elements are created, each generation knows something about the previous generation. And so you can create these, what one could reasonably call stellar phylogeny, and you can see just trivially there's two sorts of stars. Hey presto, this is the evolution of the thin disk, this is the evolution of the thick disk. This project is led by some former colleagues of ours who are now based in Chile, and so my favourite way of presenting this is making these trees that look like this, which is rather like a koipu counting stick for those who know. And again, you can see just by a glance different histories for different starts of populations. And over here are some of the people. We work with Rob Foley in stellar anthropology, and here's Rob explaining to what happens if you're not a good student. So this is the yet another of the many new ways in which we can explore very high-dimensional space, and I think this one's going to be quite fun. We haven't got very far yet. Now let me just end with the end. What's going to happen next? Well, as I said right at the start, the Milky Way and its neighbours and Andromeda and its neighbours are approaching each other at about 100 kilometres a second. And so in about 4 or 5 billion years, 3, 4, 5, depending on the details of where the mass is, which we're not sure about, the two will meet. And this is what's going to happen. So here's a picture of two spiral galaxies. This is about 1 billion years after they first interact, and you see stuff splashed all over the place, but the inner remnant spiral is still in there. And then wait for another 1 billion or 2 years and you'll end up something like this, with all the stars pretty smoothly spread out and just a little bit of debris that will then disappear. Eventually over time it'll make the last generation of new stars, and that will be the end of it. This will just be a dead stellar system slowly dying with nothing going on. You don't have to worry about it because you'll be dead long before then, because at the same 2 billion year timescale is when our sun starts to change its evolution, and it will get bigger and brighter and hotter. And it will very quickly, around that time, the sun will get hot enough that the Earth will boil dry, our atmosphere will boil away, and so we'll get the famous choice of dying by fire or dying by ice, but it will happen, and the Earth will then die, and so we will be a dead remnant in this picture. So this is the summary of everything I've said, but let me give you a better summary of how we've got where we are over the 100 years since we discovered that the Milky Way was not on its own, and that's this. It is the product of vast amounts of work by a huge range of people doing everything from building technology, developing software, to being really brilliant at managing high-dimensional data sets. Thank you.